All right, everybody, welcome back. So you're surviving the Moogle experience. That's what it's more like really coding, by the way. Lots of support code with lots of bugs in it and lots of vague specifications and deadlines that you've got to meet, that kind of stuff. That's the real world. The only thing that's more real is your final project, where there is no nice specification of what you want to do. And whether you succeed or fail depends upon how impressive a thing you put together, right? So if you haven't, you should have turned in a project description on Tuesday. We decided that it's probably more important to give you immediate feedback on that project before you have to turn in any kind of specs. So we're pushing the spec deadline back to after spring break. That doesn't mean you shouldn't start working on it. And in fact, the ideal thing is to go ahead and submit something before break to us. If you do, we promise to look at it and give you feedback. Okay? And that way, you'll be ahead of the game when you have to submit it for real after break. After break, if we're not happy with the kinds of specs that we're getting, we'll send them back to you. Okay? So think of this like an English class. You submit a paper, it's written in a crappy way, it hasn't been thought through, you haven't really done any digging to figure out what the right algorithms, what the right data structures are. Guess what? We're just going to send it back to you to redo. And that will just eat into the time that you have to actually build the thing. So this is not something that you can put off. Okay? By the way, that's probably true for all the assignments. If you're starting on the assignment, if we hand it out on Friday night, and you're starting on Thursday, not going to work. Okay? What you really need to do is at least look at the assignment, start going through it, so that during the week, when we actually have office hours, you can go ask a TF when you're confused about something, or you can post something and expect a response. If you're waiting and trying to use up your late days, the response times for the weekend are a lot slower, and of course we don't have office hours conveniently on the weekends. So get started early on those projects, okay? The problem sets. Any questions about Moogle, PageRank? What's that? No. The project. Yes?
If there are bugs in the first part of Moogle, will they compound in the second part and we'll lose more points?
No, but two things. One is, when you're doing the second part of Moogle, you might be wise to swap back in the simple list-based implementations of sets and dictionaries that we gave you, right? Because believe me, those work. Okay? And that way you don't have to worry about whether there were bugs in your code. Second of all, I'm not going to hand out the release code, but on Thursday I'll walk through, at least for the first part of Moogle, the solutions that we put together. And we can look at them and comment on them. Actually, I didn't put them together. One of my grad students did. So we can look at them and critique their code and see how they put a solution together. Okay? Good question. All right. Well, then, without further ado, I'm going to introduce to you Ron Minsky. Ron has some cool title that I don't know at Jane Street Capital. So Jane Street is a proprietary trading firm down in New York City. Ron got his PhD in computer science from Cornell back in the early 2000s, did a postdoc working on distributed systems and in particular security-related things. And then he decided to go join what we colloquially call the dark side, right, which is Wall Street. So he went to this company, Jane Street, where an amazing amount of money flows through Jane Street every day. And one of the key things is that they have to get the code right. So Ron is in charge of all of their technical people, all the people that they hire that do the hacking, as opposed to the traders who sit around and scratch their heads and think about markets. And that code has to be right. And one of the things that's very unique and interesting about Jane Street is that almost all of their code is written in OCaml. So Ron's going to tell you why that is and some of the real-world experiences in using this language in a production environment. And you guys should look at him with a very skeptical eye and give him a hard time and ask him questions about things that you don't think are quite right if you don't believe it. Okay? So without further ado, please welcome Ron Minsky.
So Greg helpfully sort of started out with some of my introduction, because one of the things I want to talk about is the perspective from which this talk comes. And I think this is actually, as a consumer of talks, and as an undergraduate student, you will be the consumer of many talks. You should always think about what's the point of view this guy is coming from. Because people's ideas are inevitably colored by the constraints that they're under and the positions that they're in. And as sort of a skeptical consumer of information, you should always be thinking about that. But before I get to where my own biases are, let me talk about kind of what this talk is supposed to be about. The title of the talk is Effective ML, and it's actually modeled on a book by a guy named Josh Block, which he wrote about a decade ago. And it is, for my money, the best book on programming in Java out there. Josh Block is, I think his current title is the Chief Java Architect at Google. And he was previously at Sun, and he knows a ton about Java. And he wrote this wonderful little book with a collection of small observations about how to program effectively in Java. Each one is about a half a page long to maybe a couple of pages. And each one of them kind of just crystallizes a small observation about how to be a good Java programmer. And one of the things that I really liked about it is a lot of these observations are observations that someone from a functional programming perspective would agree with. For example, one of the things he suggests, which is I think a good thing to think carefully about in your programming, is avoiding mutability. Another suggestion he has is that you should avoid inheritance, that when you can get away with it, you should use containing rather than inheriting. And these are all kind of messages which someone who thinks a lot about functional programming will kind of find very pleasant. But in fact, when I first looked into the book, it wasn't from the point of view of someone who was doing a lot of programming in ML. In fact, I'd done some as a graduate student at Cornell. But actually what I was doing was trying to help people out at Jane Street in sort of getting a better sense about how to program in Java. And so now that I've actually been programming for something like 9 years in ML in actual production setting, I've kind of put together my own set of lessons. And I kind of want to talk through those sort of from the, and I think hopefully they'll be useful lessons from the point of view of people who've just started seeing languages like ML. So to the point about perspective. So what is our perspective? So one of the important bits is the thing that Greg mentioned, which is the focus on correctness. So our basic business is electronic liquidity providers. What does that mean? It means there are lots of people who have something they want to do. They want to buy something. They want to sell something. They have an axe to grind. They have some direction they want to go. They want to make an investment. They want to unwind an investment. They have a natural reason for trading in the markets. And then there are other people whose role is essentially that of middlemen, who stand in between and buy from one and sell to the other and make the entire process more efficient. It's essentially the same role that somebody who runs a grocery store has. Right? The guy who runs a grocery store, how does he make his money? Is it by making bets on the future value of tomatoes, like what the price of tomatoes is going to be in 3 months? No. He has to worry about that kind of stuff because he has to think about how much his inventory is going to cost. But he primarily makes his money by buying it at one price, selling it at a somewhat higher price, and making money from that gap in the price. Right? So if you run a grocery store, you might call that gap the markup. If you were a bookie, you'd call it the vig. And if you were a trader, you'd call it the spread. But it is fundamentally the same role. It is the role of the guy who stands in the middle. And one of the aspects of that role in an efficient and competitive marketplace is that the edges are very thin. Right? You make very little on each trade that you do. Fractions of a penny could be the sort of size of the P&L that you make on an individual trade. But how do you have a good, profitable business out of it? You make it up on volume. And we do a lot of volume. There are billions of dollars of money that are traded back and forth in the systems that we run every day. And it's kind of terrifying, right? I mean, if you don't feel a certain kind of existential fear at doing that kind of business through a computer, you are not cut out for this kind of business, right? It is a terrifying thing to do. And there's no faster way of lighting yourself on fire than to make a small mistake over and over in a tight loop. And when you have lots of highly efficient systems doing lots of trading in many venues with a very complex environment, it's easy to make those mistakes. So the focus on correctness is a big deal. That said, correctness isn't the only thing that we care about, right? I think you can, I always like to mention the example of you'll hear these stories of like how NASA creates software. And it's really interesting. They use all sorts of extreme methods to make really sure that their systems are programmed correctly. And even then, they don't always get it right. But the reason, and the reason that they work so hard at it is that it is enormously expensive to make a mistake, right? You know, if the rocket kind of goes the wrong way, like that's a pretty expensive and embarrassing mistake. And they work very hard to avoid it. And an ordinary software engineer can be forgiven of looking at this and thinking, that's really neat, but I'm never going to do that, right? Because I just don't care that much, right? If the web server that I create, like it turns out it fails 1 in 10,000 times, it's like, well, that suggests that I put an appropriate amount of effort in getting it right, because it's just not that important when it fails. So this is why I want to emphasize that our point of view is not only about correctness. There are lots of things that we do that are very correctness critical, but there are lots of things that we do where getting things done quickly is the most important thing. We have a big research infrastructure, and if you're doing kind of research into markets, then quick turnaround, rapid prototyping is the name of the game, right? You want to be able to put things together quickly and efficiently. And we care a lot about that, and we use OCaml for those applications as well. One way in which we are quite different from lots of other companies that build software is that we depend much less on tying into other people's software. This is not to say that we don't tie into other people's software at all, but we are not like building fancy websites, right, for which it's a big advantage to tie into lots of big existing toolkits for doing that. We don't even build lots of fancy desktop UIs. And in fact, the vast majority of the things that we do are software that we've built ourselves kind of from the ground up. Obviously, there's some, we didn't write our own operating system. But the vast majority of the code that goes into our system is code that we wrote. And we can change all of it. And I think the ability to be kind of off on our own and have very big, very complete control of that code base has affected our technical decisions a lot. I guess the one other thing I want to mention about the point of view that we have on all of this is the way that we think about code and what the purpose of code is. For lots of purposes, the right way to think about code is a way of getting stuff done, right? You have tasks to achieve. You have your search engine to write. You have some website you need to build. You have some calculation that needs to be done. And you build software in order to get the job done. Because of the concern that we have about the correctness of the code, we also care a lot about code as a means of expression. When we care about being able to look at the code that's written and understanding the intent of it and understanding what it's supposed to do and being able to think deeply about its behavior. And the reason for that is, for a lot of the things that we do, testing is not really enough. The reason that we're always leery about testing as a kind of complete solution to thinking about whether or not your system is correct is that in financial markets, the kind of the distributions of events that you see is not what you see in lots of other places. You sort of, in the natural sciences, you expect many things to show up on a normal distribution. And one of the properties of a normal distribution is the tails of that distribution fall off very quickly, right? And what that means is that you can sort of sample, get a reasonable number of samples and get a fairly good overall shape of the distribution. But for much of what happens in the financial markets, and I think as has been in great evidence over the last few years, there are events that happen that are deep off in the tail of the distribution, and they happen a lot more often than you would think. Crazy situations show up in financial markets with somewhat alarming regularity. And if you want to be robust to those kind of events, it's not enough to test, because it's never going to happen in your testing. Right? You need to think from first principles about what your code's going to do and about what's possible. And in order to do that, you need to have code that you can actually think about, that you can actually reason about. And I think that part of our approach, more than anything else, has colored the way that we think about software development. OK, so let me get kind of to the actual meat of the talk, which is these individual lessons I want to talk about. And the first one is just a natural extension of the thing that I said before. So at various points in my life, I have spent almost all of my time writing code. And as time has gone on, I have spent more and more time not writing code myself, but reading other people's code. And I have noticed a shift in my own ideas about what makes sense and what doesn't make sense, and similar shifts in the conceptions of other people I've worked with. Right? And if you sort of naively break up people into readers and writers, writers are people who just write code, and readers are people who also do a lot of reading, there are often systematic differences in what readers want to be done and what writers want. And the basic rule of thumb that I have is the readers are right and the writers are wrong. Right? People who spend most of the time writing their code value their own convenience, and readers value their own convenience. But it's the convenience of the readers that really matters. And the reason for that is aiming towards code that's easy for reading promotes a number of really important things. First of all, it promotes code that's correct. Right? I think what's the there's a sort of standard phrase about this, like something could be so complicated that there are no obvious bugs, or it could be so simple that there are obviously no bugs. And in order to get stuff that really holds up, it's important that it be simple. And simplicity is something that readers often go for, because the whole point of reading a piece of code is to construct an informal proof in your head that the code does the right thing. And that's really hard, and it's really, really hard if the code is complicated. But it's not just about correctness, it's also about agility. Code that is simple is easier to change later. Right? And being able to change later is also very important. I think people in college spend a lot of time writing a project. You go to a class and you write a project, and then if your professor is very forward-thinking, he will, and maybe this is increasingly common, he'll give you the project and then make you do a later set of changes that he doesn't tell you about at first, right? So to encourage you to write general code. So this is sort of a nice exercise, but in the real world, you do this over and over and over and over and over and over and over again, right? A single piece of code is read and modified many more times than it is written in the first place, right? So it's very important to aim for code that is as easy as possible to read. And as you'll see as we go through these other lessons, the idea of favoring the interests of readers over the interests of writers kind of permeates the discussion. By the way, to echo something that Greg said, please, I've said nothing particularly technical yet, but when I do, somewhere between half and 3/4 of you are going to be lost, and none of those people who are lost will ask a question, and then that'll just be a sad out. So please ask actual questions when you are confused. I assure you there will be other people who are more confused than you. Okay, so that was fine for a kind of very high-level idea. Now let's talk about something very concrete. So the lesson here is to create uniform interfaces, and this is kind of a 2-for-1. The first suggestion here is create interfaces. So what do I mean by this? So in ML, in OCaml in particular, there's this two halves of the code, right? There's the ML, which is the implementation, and the MLI, which is the signature. And it's very tempting, especially when you're doing a project on your own, it's just kind of your own thing, to just kind of work on the implementation and not really bother with writing all these interface files. It seems like a certain amount of duplicative effort, and it doesn't really change what the program does anyway, so it's not that big of a deal. And I, in fact, did this myself. When I first started at Jane Street, I wrote a bunch of code that I was pretty sure I wasn't staying. I was going off back to academia, and all the code was going to be thrown away. And 80,000 lines of code later, it turned out it wasn't all going to be thrown away. And one of the things that's symptomatic of that code, which I am embarrassed about when I go back and look at it now, is there were no interfaces in sight. It's like, there's this great type system, algebraic data types, type inference. Who needs interfaces? And it turns out I did, right? It turns out not having the interfaces kind of works when you get started, but is a disaster for anything that is going to live for a significant period of time. So I think it's one of these things where I kind of uniformly tell people who work at Jane Street, it doesn't matter if you think you need it, write an interface. So I think this is sort of broadly good advice. But it's not enough to write interfaces. You also have to write good interfaces. And one aspect of good interface design is to make the interfaces uniform. Right? In other words, to have the same kind of patterns appear over and over again in the interfaces. So, for example, when you have a function like list.map, right, which I imagine you guys are mostly familiar with, you raise your hand if you know what list.map is. Sweet. There's also array.map. And maybe, I don't remember in the standard library, set.map. Any different kind of container, you can have this kind of map function associated with it. And if you design your interfaces well, all of those maps should basically have the same type of signature. Right? It's one simple kind of uniformity. Actually, one other kind of uniformity is they're all called map. Right? The things that encapsulate what is logically the same kind of operation also have a standardized name. So this kind of standardization is very useful because what it means is a programmer coming to a new piece of code has a big leg up. Right? They can just kind of look at it and have solid expectations for how things are supposed to work. And those expectations sort of reduce the kind of impedance mismatch between how they think about the world and how this piece of code thinks about the world. You don't. One thing I tell people that they should avoid is the situation where someone looks at a piece of code and like, oh yeah, that's John's. Like I know that's John's code because he always does this crazy stuff that's not like anybody else, right? And you want to have a certain uniformity to make it easy for people to think together because programming is a collaborative effort. So you can yell at people, like you can encourage them to create uniform interfaces, but it's also nice to give them tools to do it. And what I want to do is just show you one simple way to encourage uniform interfaces that we use. And that is through the use of what I'll call interface components. So the idea is you can have standardized chunks of a signature that you then reuse in lots of different signatures as a way of kind of putting a standard face on a module. So here's an example of what a signature might look like that would kind of wrap up the idea of comparability. So here you have a function called compare, which takes two arguments of type T. And here, the type T is the type of whatever module corresponds to the thing you're dealing with. So it might be an int.t or a float.t or a list.t or a car.t. There are lots of different places you might use it, but in all of these cases, there's going to be one particular type that you're talking about that's being compared. So after this core compare function, there's a bunch of essentially helper functions which can basically be derived from the original compare, such as the infix operators and a min and max function. And then at the bottom, you'll see these modules. These are actually specifying submodules. So part of being comparable, according to this interface, is having a map and a set module which use the type in question as a key, and use the comparability associated with this interface as the key there. And what's nice about this is then kind of a drop-in component. You want to say that this is comparable, you just kind of drop in this part of the module interface, and let me give you an example of that. Right, so here's what the interface for the character module might look like. And then what happens is you now have this sort of one-line thing guarantees that you have the standard naming conventions with respect to comparisons. And if you violate those conventions, your module will not compile. And there's no better incentive to getting it right than saying your thing won't compile. Right, and you note here, what I sort of in this car example, I've included a number of other standard components. So there's comparable, there's stringable, there's hashable, like all kind of relating to different kind of capabilities you could have relative to a type. There's actually another idiom embedded in here, and this is the idiom of by default, taking your types and wrapping them up in a module and naming the type a standard way, calling it a standard type T. And one of the reasons it's nice is it makes it easier to do this kind of standardization. And if you use functors, it makes it easier to use functors with your modules. By the way, have functors been covered in this class at all? Great. So having this kind of standardization means that you don't have to like create a new ad hoc module to make it kind of fit into the interface. It means that you can have a functor that just takes anything that's comparable and stringable. And since it's a standardized way of expressing those, no further work needs to be done. Any questions? All right. All right, so make illegal states unrepresentable. So this actually comes back to why it's worth using a language like ML in the first place. I think when people come to ML for the first time, or a language like ML, and in particular when they come to it with a lot of experience in other languages, they have the following kind of starting misconception about how things work. They think, well, there's this language which lets me do things, it has various kinds of instructions, and then hovering above it, there's a type system. And the type system enforces constraints on the underlying language. And sometimes this is great because it catches bugs. And sometimes it's terrible because it stops me from running what are in fact perfectly well-formed programs that the compiler is too stupid to understand. Right? And so a lot of people who think, well, I'm a smart programmer and I don't need this compiler getting in my way, and I'll program in C instead. And I'm just kind of smart enough for this not to be an issue. There's a number of sort of hubristic elements of this story, but the fundamental error here is that this all comes from thinking of the type system as a constraint system that runs at the end and not a tool. And in reality, the type system, as any decent ML programmer needs to learn, the type system is a tool in itself which you need to think about and engineer as part of the engineering of your program. The type system allows you to enforce invariance on the program. And that is useful whether you are trying to make sure that the first time you write the program, it is not buggy. And it's also useful when you want to communicate to somebody else. It's useful when you want to put constraints on the evolution of a program. And it's useful when, 2 years later, some dummy wants to use it who doesn't understand what's going on and makes changes that don't make sense. And it's especially helpful when that dummy is you. Right? When 2 years later you are using some piece of code that you have forgotten how it works, having these constraints in place is a very powerful thing. So one kind of rubric we use for how to think about using the type system is to try and make states that are illegal in your program to make them unrepresentable in your data types. Right? And this is really one of the ways of thinking about this is really a kind of suggestion about how to use algebraic data types. So let's pull up another example. So here is a pair of data types, an algebraic data type, all in having to do with the state of a network protocol. So there are kind of two pieces here. There's this type called connection state, which is a variant, right, a disjunction, telling you what state your program is in. And then there's this record, connection info, which has a bunch of other miscellaneous information about the state of the connection. It tells you, it contains, right, containing, right, is not inheriting, but it contains the connection state inside of it. It also contains the address of the server that you're connecting to. It has this last ping time and last ping ID. And the idea here is that this could represent in lots of protocols you have a notion of pings being used to kind of keep alive a connection and make sure it's up. And here you just keep track of the time that you last saw a ping and the ID of that ping that you saw most recently. There's a session ID, which is a unique identifier for the session. And then two times. One is when initiated, when you started trying to make the connection, which is useful for deciding whether you want to give up at some point. And when disconnected. If it was disconnected, when that disconnection happened. So just to kind of throw this out there to you guys, did anyone have any thoughts about this? Any questions about it? Oh, sorry, that is actually an Emacs hack for folding and unfolding sections of the code. So that's yeah. So you see that ... down there? That's like more code I'm going to open up later. So nothing too interesting for the actual content. So how does this differ from how you might model it in Java? Have you guys, Aki, raise your hands if you guys have seen Java yet? All right, so about half of you guys, it looks like. So one of the things to note here is that one way that this is different from what you'd see in Java is we handle the notion of null very differently. In Java, there's this idea that everything might be null. Right? Every object reference could be a null reference. And in ML, that's not how it works. In ML, there's an explicit notion of something being an option type. Right? So where you want to express the fact that something might not be there, you explicitly mark it as an option. You'll notice that all but two of the fields up there are options. Right? And they're options because it's not clear that you actually need all of that information, that you have it available to you at every point in time. For example, before you've received your first ping, you're not going to have a ping time or a ping ID. Right? But if the connection's never been disconnected, you're not going to know when it was disconnected. Right? So the optionality here explicitly tells you where things might be nullable and might not be nullable. And in some sense, that's a step up from the Java implementation because it's at least explicit. It warns you in the type when things might not be there and forces you to explicitly handle the fact that it might not be there. On the other hand, when you have options everywhere, you're not really in such a great state, because it means you have to do a lot of checking manually to make sure that all of the information is kind of in the position that you want. And in fact, there's a bunch of tricky little invariants about when things should and should not be present. For example, if you have a last ping time, you should probably also have a last ping ID. Right? Those two kind of go together. And, well, the session ID, before you've actually fully connected the session, you're not going to have one. And after you fully connected the session, you'd better. Similarly, when initiated, after you've finished initiating the calculation, the connection, you probably want to throw that away. You probably don't need that anymore. And when disconnected, you certainly don't have until you've actually disconnected for the first time. Right? So there's a bunch of invariants about how this should be organized, and they are not reflected in the type. Right? They're just things that you have to know. And every time you walk in to write a new function that manipulates this, you have to think, oh, I got to be careful. Right? I have to make sure there's a nice big comment at the top of the module which tells me what all the invariants are. And every time I write a function that transforms one of these, I have to make sure all the invariants hold. Because if I don't, I'm going to get it wrong. Right? It's very error prone. You can easily make mistakes. So you have to be very explicit about what those are in your comments and be careful about it. So in ML, happily, there are natural ways we can transform this to get rid of some of these invariants, in the sense they still need to be there, but you can make it so that you don't have to do them kind of by hand. So, oops. So here's a rewritten version of this interface, where I've kind of taken the data structure and turned it inside out. So what's going on here? So first of all, at the top, I now have these three types: connecting, connected, and disconnected. And these types basically represent the information that you have to have in each of the three different major states that a connection can be in. And then, instead, so before I had this connection state type, which just kind of was like an enumerated type. It said, here are the names of the three states. Now, the connection state type has three arms, but the three arms actually contain something, and they contain different things in each of the cases. Right? So when you're in the connecting state, you have the connecting information. Connected, you have the connected type. Disconnected, you have the disconnected stuff. So that is kind of ties up with the types right above. And then the connection info now just has two fields. It has the state, which is that type above, and it has the server. And the server is now kind of the only thing from the original design that stuck around. And why did the server stick around? Why does that stay where it was before in the top level type? Because it's always there, right? So what's basically happened is we've kind of taken all the stuff that depended on which state of the variant you were in and pushed it down, right? So that it only showed up where it really mattered. And now, basically all the invariants I talked about before are kind of naturally just held together by the data structure itself, by the algebraic data type. There's one other small thing I did, which if you look at the last ping, so the last ping is still an option, but it used to be that we tracked the ping as two different values. There was the ping ID and the ping time. And now we've converted them into a tuple, where they're either both there or both not there. So that's another, so there's like a little extra knobby that's in there, a little extra piece of structure that captures the fact that those two fields are tied together. So I actually gave this talk in this class last year, and someone asked actually a very good question at the time, which was, can you always do this? Right? Can you always take the invariants you have and pack them into the data structures and thereby improve your life? And the answer is, for sure not. You cannot always do this. There are lots of cases where you'll end up with where you have to do the dance I talked about before of being very careful and explicit about your invariants and making very sure every time you have a function that comes in and out that those invariants are maintained. But it is surprisingly often the case that algebraic data types are a rich enough language that they allow you to encode the most important invariants of your program. So it's by no means always, but it is an almost shockingly effective tool. And I think it's not effective kind of at random. It's effective because there's something deep about the whole idea of algebraic data types. And something deep which kind of surprisingly most of the programming language world seems content to live without. There are these kind of two kinds of constructors you have in ML. You have the notion of a product type and the notion of a sum type. Right? A product type is the thing that every programming language supports, a record. Right? I want this and this and this and this, and I want them all together. And a sum type is just the dual to that. I want this, or that, or the other, and an or, right? And it turns out in lots of kind of mathematical systems have these two linked operators, which when you sort of combine them and layer them with each other, you can build really rich logical structures. Right? And this is true whether you're talking about and and or in logic, or plus and times in arithmetic, or universal and existential quantification in logic. But you have these when you have these kind of two operators that kind of tie together, it gives you really rich structure, and that structure turns out to be very, very effective in programming. So that is basically what I have to say on that. So does anyone have any other questions about this example? All right. So this is a very closely related idea, and this is the idea of trying to code for exhaustiveness. So what do I mean by this? So it turns out OCaml has some very nice guarantees provided by the compiler for guaranteeing that your code exhaustively enumerates a set of possibilities. In particular, when you do a match statement, the compiler statically checks that, and even though matches are, there's a quite rich pattern matching language, you can do pretty complicated expressions, the compiler can always look at one of these and tell you whether or not the matching is guaranteed to be exhaustive, whether you might have missed any cases. It also warns you whether or not there are duplicate cases, or it'll also warn you of impossible cases, things that you write down that kind of don't make sense, don't hold up given the data structure in question. And this turns out to be an extremely powerful tool. It's both useful for getting your code right in the first place, but where it really shines is as a constraint on the evolution of a program. You could think of it as what's often called a refactoring tool. Because what it means is the fact that the compiler will check for exhaustiveness means that when types change, the code that manipulates those types will no longer compile until they can take into account the changes in the types. Now, ML is very, very good at this, but it's not so good that you cannot defeat it. You can write your code in a way that defeats these exhaustiveness checks, and if you do, you're kind of on your own. And so the core of the suggestion here is to think carefully about exhaustiveness and think about the guarantees the compiler provides when you write your code, and write your code in a way that gives you the best possible guarantees. So, give yet another example. So this is a financial example. The idea is we have a type message, and the idea that these are messages that might be being sent back and forth to an exchange. And there are three types of messages contemplated here: an order, a cancel, and an execution. So an order is basically someone's expression of willingness to enter into a trade. I am willing to buy IBM at a price of $35.50 or better, and for up to 1,000 shares. That's what an order is. A cancel is the negation of an order. It's like, I'm out. I'm no longer willing to honor that order. I want to cancel it. And then the final bit, the execution, is if two people have orders such that there's a price in between the limit prices that they've expressed, there's a trade they're willing to do, then an execution will go up on the exchange, and you will be delivered an execution message, which basically says, now a transaction has occurred, the world has changed, you have more of the security in question and less money if you bought it, or less of the security in question and more money if you sold it. Right? And so that's what the execution is about. And the execution changes one important thing, which is what we would call the position, meaning how much of the security do you have? Right? Sending an order doesn't change your position, but when you get filled, when you get an execution, you bought that 1,000 shares, whatever your old position was, it is now 1,000 bigger. So one natural kind of function to write is something which takes one of these messages and computes the effect of that message on your position. And there's some code right here to do that. So the details of the code aren't enormously important, but the key thing is this match statement. And you take the message, you match it, and you see if it's an execution, which, as I said, is the only one that can change your position, then you do a little calculation to figure out how much your position is changed by, and you return that. And otherwise, you return 0. Right? Because it didn't affect your position, so the change is 0. Everything's good. So the code is pretty terse, it's pretty clear, it seems like it's not much of a problem, but the problem comes up when things change. So imagine now that someone decides that we have not done a good enough job of modeling what might happen on the markets. In particular, they added another type, what's called a correction. A correction is where the exchange says, that execution I gave you before, I kind of made a mistake. you said you wanted to buy 10,000 shares of Apple. Actually, you sold 5,000 shares of IBM. Sorry, didn't work out. Right? The correction is usually not to a different security, but there are certainly corrections where it says you thought it was this price and now it's that price. You thought it was this size, now it's that size. That's a sort of common, ordinary occurrence in markets. And now, what happens when someone adds that new variant to the type? This code is now wrong. Right? It used to be right, but the type changed, and the code has silently gone from being right to being wrong, and no one would necessarily have noticed it. And one of the reasons that no one might notice it is because, like right here, they're right next to each other. It's like obvious. Like when I go and change the type, obviously I should change this code that depends on the type. But this function might be somewhere far away in some other file, or thousands of lines away in the same file. You really want the system to help you to find these cases where you need to make these changes. And you could have changed the original code in a very simple way to get that. The thing that you do, the thing that kills you really in this code is this underscore here. It's this catch-all case where I said, and for all the other cases, whatever they are, trust me. I know what the answer is. Don't bother me, compiler. It's 0. Right? And if instead you're just explicit about it, you're in a much better place. Because what happens now is if we had started with this code and then made that change to the type, the compiler would no longer have allowed this to compile. It would have said, sorry, you only contemplated execs, orders, and cancels, and there's another case that you haven't thought about. So the basic advice here is to think about, as a broad thing, think about these exhaustiveness checks, and generally think about the checks the compiler does for you. And in particular, in match statements, you should really try and avoid catch-all cases. Underscores are, so having an underscore at the bottom of your match is usually a sign that you have done the wrong thing. There are cases where it's the right thing, but 90% of the time it's a mistake. Okay, so here's another one. Open few modules. So there's this nice feature in ML where you can do what's called opening a module. When you open a module, it basically dumps that namespace into the present namespace. And this is, for what it's worth, not just a feature of ML. Java and Python and sort of almost any language you can name has this notion of taking a namespace and kind of dumping it into the namespace of the current piece of code that you're writing. And it is a very convenient feature because it allows you to kind of make all of your code a little bit terser, right? And long code, the longer your code is, other things being equal, the longer your code is, the harder it is to read, the harder it is to understand what's going on. But in this case, not all things are equal. When you open a module, you are trading off terseness for explicitness. Right? You're making your code more terse but less explicit. It's now harder to look at any piece of code and figure out, well, where did this function that I'm calling come from? And that's not too bad when you open a small number of modules. But it's fairly common practice in lots of languages. Like the top of the file is like somebody opening 30 modules, right? And this is one of these cases where I can see why you'd want it as a writer. But as someone who's trying to read the code, it's horrifying. Because you look at the piece of code, you have no idea which of these 30 modules to turn to figure out where the thing in question came from. And to be clear, you can get some help from this from tools, but it's still a problem.
If you have the proper IDE,
so it's less of a knockdown case that you need that you should be clear about it. I think it is still an issue in that I do think that being able to read a piece of code kind of in a straightforward way without having to hover over everything and figure out where the types are from. To be clear, these are not IDE things that we don't have at our disposal. There are tools that we have that allow us to kind of take any value and immediately figure out, pull up the source file from where it came from, figure out what type it is. But even with those tools at your disposal, I think having the code be clear and explicit about what it's doing is helpful, right? It's also easier to kind of move code around when it's not enormously dependent on its kind of local context. Now, I agree that the IDE stuff helps a lot. But the other thing is that the cost in terms of concision is not as bad as people think it is if you use the right idioms. Right? And that's kind of the other thing I wanted to say, is to kind of pull up an example of what I think is a useful idiom for dealing with this. So here, so I don't expect you to read all of this. I'll just point out some kind of relevant features. But this is my implementation of true. True is a highly important Unix utility. It is, as the documentation says, it is a command that does nothing successfully. There's also false, which does nothing unsuccessfully. But I'm just implementing true here. And this is actually a kind of high-powered version of true. It has lots of features, which even GNU true doesn't have all of these features. So, for example, there's a little command line parsing library that's at use here to give it a couple of different arguments, one for specifying an exit code and one for specifying a message for it to print out when it runs. So the thing to note is, so what have I done? At the top, I've opened up 3 modules. Core.std, which is a kind of the standard, that's actually this kind of our standard library component. And then it opens this library called command and another library called flag. And why do we do all this opening? Well, it turns out, if you look at over here where it says flags, oops. So each one of those lines in the list has this int and string at the beginning. And these are actually, those are not types. What those are these are actually what you might call, if you wanted to be really fancy, type indexed values. They're basically values from the flag module, which tell you how to parse a value of the given type. And they're really functions that take arguments that tell you how to that allow you to specify the thing being parsed. And it turns out that the module flag is actually a submodule of command. And so this would get pretty ugly if you wrote the whole thing out. You'd have to write command.flag.int and command.flag.string. But if you just kind of look at this visually, it's not at all obvious that flag is in fact from command. Right? And we open command and we get some things out of that. We open flag, we get other things out of that. It's like the code is reasonably terse, but it's also a little hard to figure out where the different pieces are coming from. So it's quite easy to write this in a way that doesn't really have this problem. So basically all I did was instead of opening the modules at the very top scope, what I did was down over here, I renamed the module. I use this let module construct in OCaml to give the module a local name and then use that local name in all the places where it's necessary. So now I am fully explicit about where everything is coming from. I haven't added an enormous amount of verbiage to each of those lines. It's still pretty easy to read. And the other thing that's notable is the names that are introduced in a small scope. And I think this is actually an important thing to think about when programming, when you're trying to program in a way that is easy to read, you need to respect the cognitive limitations of humans. Right? People are not very smart. Right? They cannot remember very much. Right? You give them, you tell them 7 things, and the first 3 of them fall on the floor. Right? If you're going to force people to remember things, you want to give them clear clues as for how long they're going to remember it for, so that they can forget it, they can let go. And that's what this does, right? Let module f equals command.flag. You need to remember that until the scope ends. And the scope ends very soon. And when it's done, you can forget that alias. Right? In fact, this is a somewhat unrelated point, but when you're thinking about how to name your variables, some people like to name variables with very short names, like x or y. And some people like to name variables with names that are as long as your arm, right? Command flag interpreter or something, right? And sometimes you feel like you should do one, sometimes you feel like you should do the other. One good heuristic for thinking about it is think how long-lived the name is. If the name lives for a very short time, in a very small scope, give it a short name, because people will remember. If it lives for a long time and spreads over a lot of your code, give it a long name, because people are going to need to be reminded, and the name is a useful reminder. Any other questions about this? Yes?
What are all the tildes?
Tildes. Oh, yeah, this is another feature of ML that maybe you guys didn't see. These are labeled arguments. So in OCaml, there are 2 ways of passing arguments. You can do it by position, so that the first argument has this meaning and the second argument has that meaning, or you can do it by names. And we at Jane Street actually do a lot of use of named arguments, because one of the key places where it's a good idea is where the type doesn't tell you very much about the meaning of the thing being passed in. For instance, you might have a function that's supposed to take a sub-range of a string. And it takes 2 numbers, the position and the length. Which one is which? Well, if you label them, then it's really clear at the call point which one is which. And if you don't, it's pretty unclear. Another good example is you need to pass in a flag to something. It's a bool. It's true or false. It's like people often, when they first write it, think, oh, it's clear what true should mean and what false should mean. But it's often not clear. Right? And you get this argument passed in as true or false, and it could easily be one way or the other. It's often hard to guess. And giving it a clear name and forcing that name to show up at the call point is a very big aid to the people who are reading the code. Right? And again, one of the things I think when you design an API, you should be thinking about the call point. Don't just think about the interface file. Don't think about the documentation. Think how it looks in the source. Think how it looks when it's used. Because most of the time, people are too lazy, because in addition to being not too smart, people are also lazy. People are too lazy to go to the documentation. They will look and they will read and they'll stop there. And you want to give them as much of a clue as what's going on as you can at that point.
So when you actually call the function, do you say like the argument values?
So if you look here, right, so here it's tilde summary colon does nothing successfully. So that's the style that's used there. There's also a thing called label punning. So it turns out if there was a variable called summary, you could just do tilde summary and nothing else, and it would know to pull that one in. So tilde summary with nothing else is sort of equivalent of tilde summary colon summary, basically. So it's actually, if you have your variables named in the right way, it's actually syntactically very lightweight. It amounts to just putting an extra tilde in front of things. And it actually does another nice thing of it encourages people to name things the same way in lots of different contexts, which again is useful for having a kind of intellectually coherent code base. Okay, so I think probably about now we should call a break for a few minutes, and we'll pick up in about 5.